Hello everyone, welcome to the lecture series Foundation for Wheel Side Design. This is fourth lecture. In this lecture, we'll be continuing with the digital systems. Specifically, in this lecture, we'll be looking into sequential circuit elements. First, let us look into a rudimentary memory element which can be implemented using a cross-coupled inverter pair. So what is a cross-coupled inverter pair? So it consists of two inverters, G1 and G2, and the output of the first inverter goes to the input or to the second inverter, right? Now, in this inverter pair, if we apply the input voltage of 0 volt or logic 0, then it will produce, G1 will produce an output of logic 1 or output voltage of VDD. And the second inverter G2 on receiving the input voltage of VDD will produce an output voltage of 0 or logic 0, right? So given an input logic of 0 or input voltage of 0 volts, it will the cross coupled inverter pair will produce an output of 1, right? Or the logic 1 or equivalently voltage level of VDD, right? Now, if we instead of the input having a voltage 0, if the input voltage was say VDD or logic 1, right? In that case, the first inverter will produce a logic 0, and on receiving a logic 0, the second inverter will produce a logic 1 at the input. So now the out given the input voltage of or input logic of 1, the cross coupled inverter pair will produce an output of 0, right? So now this cross coupled inverter pair reaches stable states 0 or 1, right? And there is a positive feedback from the output to the input. So meaning that the whatever the voltage was there, right? Whatever the voltage we had applied, for example, in this case, we had applied the input voltage of 0 volt, right? So the output was VDD, and this output was actually reinforcing 0 volt at the input, right? And similarly, if the input was VDD, then the output or the second inverter G2 is reinforcing the same value at the input. So in a sense, there is a positive feedback from the output to the input. And what is the impact of this positive feedback? The impact of this positive feedback is that even if there is a small noise in the system, the state will not change, right? For example, if the input fluctuates and there is some small voltage change at the input, so instead of say 0 volt at the input, it was slightly say 10 millivolt or so, right? So this small change in voltage will will actually get cancelled out by the second inverter G2, which might be forcing it to the input towards 0 volt, right? So since the input is say 10 millivolt, it is very low, so it will be still considered as logic 0. The output produced at by this cross coupled inverter pair will be around say VDD, right? It will be producing a logic 1 at the output, and because of VDD at the input of G2, right, G2 will produce an output voltage which will be very much close towards 0 volt, and it will, if the input in was was changing slightly away from the ideal value of 0 volt, the feedback mechanism will force it to go towards the 0 volt, and therefore this condition that the input 0 output 1 and input 1 output 0 is a kind of a stable state. And and once the one of the stable states is reached, it can remain in that state for indefinitely long time. and therefore this is a kind of a memory action. So once it reaches the state 0 1 or 1 0, then in that case this even if we remove the input, right, or even the input has got some noise, the cross coupled inverter pair will remain in that state, and and therefore this is a stable state, and it is a kind of memory action. So that even if the input is removed, the the cross coupled inverter pair can remember that what was the other initial value that was applied as input to the inverter pair, and it is remembering that value, and it is therefore there is a memory action. Now there can be another state in this cross couple inverter pair, and that is what is known as metastable state. Let us understand what is this metastable state, right? So if we consider the inverter, right? So inverter typically has a transfer characteristics which is shown in this figure. So on the x-axis we have VA, that is voltage at the input, and on the y-axis we have VDD, we have voltage VZ, which is the output of this inverter. So whenever the input is less than some threshold, then the output is VDD, right? And whenever the voltage is high, whenever the input has a high voltage or logic 1, then the output will be close to 0 volt, right? So this is the characteristics, and in the intermediate region there will be a sharp transition from 1 to 0. So this is how the transfer characteristics of inverter pair will look like. Now in this transfer characteristics, if we draw a line, Vz is equal to Va, then this is a straight line with a 45-degree slope, meaning that Vz is equal to Va line. So it will cut the transfer characteristics at this particular point, right? So this particular point is the point at which the voltage at the input and the output are the same, right? And this is known as Vm. From the transfer characteristics of the inverter, we can extract a voltage Vm, that is this voltage, such that Va is equal to Vz at this Vm, right? So a cross coupled inverter can take another state, Vin is equal to Vout is equal to Vm, right? So if we apply Vm as the input if we apply Vm at the input, right, then what will be the output produced by G1? So as per the transfer characteristics, it will be Vm, right? And if the second inverter is implemented in the same manner, so if the second inverter is getting an input as Vm, then it will produce the output as Vm, right? So the V input is equal to output is equal to Vm. That is another state, right, in which the cross coupled inverter can exist, right? So now if there is no noise in this system, then the cross coupled inverter pair can remain in this state, Vin is equal to Vout is equal to Vm forever, right? But that is very idealistic situation, right? Real real uh, systems will have some noise, right? And if there is noise, what will happen? So will it still remain to will the cross coupled inverter will still remain in the state Vin is equal to Vout is equal to Vm, or it will go to the 0 state or 1 state? What will happen? So let us investigate or examine this aspect of the cross coupled inverter pair. So if there is a small noise, it gets amplified at the point Vm due to high gain of the inverter at this point, right? Now, if we look into the transfer characteristics of the inverter at this point Vm, at this particular point, the gain is high. What is gain? Gain is basically, we can define gain as delta Vz by delta Va, What does this mean is that V gain is the change in amount of output that is accomplished by change in voltage at the input, right? So delta Vz is the change in the voltage at the output, and delta Va is the change in input, right? A change in the voltage at the input. At this particular point, the slope is steep, right? The slope is steep, meaning that if we make a small change in Va, there'll be a large change in Vz, and therefore we are saying that at this particular point, the gain is pretty high in an inverter, right? Now, because of this high gain, what will happen? Let's see. The cross-couple inverter finally reaches one of the stable states due to the noise, right? And depending on the noise value. So the noise gets actually amplified, and the inverter pair will reach either the state 0 or 1. Why it will happen? Let's see. So suppose this inverter was at the metastable point, that is V in is equal to V out is equal to Vm, right? And let's assume that the input voltage decreases or increases slightly. Let it increase slightly. So from this point Vm, let the input voltage, that is V in, is increasing slightly, right? So V in was Vm plus delta, very small positive voltage was there, right? So because of this small positive voltage, since gain is very high, right, there'll be a large change in the output of G1, right? And where it will move in the direction towards 0 volt, right? Why? Because the slope is in this direction, right? So if we make small increase in voltage, the output voltage will decrease from Vm, and how much it will decrease? It will be gain multiplied by delta. That delta is the voltage that we have assumed, the noise voltage by which the voltage moved from the Vm state at the input of the cross coupled inverter, right? So gain into delta, by that much amount the voltage will decrease at this point, right? So now the voltage at output will be Vm minus gain into delta, right? Now this gain is a large value, so V out will move very quickly towards 0, right? And as a result, what will happen? If this is moving towards 0, this point will start moving towards 1, right? And by how much it will change? Again, the gain of the inverter will come into play. If we consider this G2, there is a large change in input at G2, and because of the gain of the inverter, the G2 will produce a further higher voltage, right? And in which direction it will be? It will be in direction such that V in moves towards VDD, right? So what will happen finally, that whenever there is a small change in noise positive voltage for V in, it will finally settle to the state in which V in reaches VDD and V out reaches 0 volt, right? So the state 1,0 will be reached in this case, right? Now, if we consider that the noise voltage was in the opposite direction, meaning that the input changed slightly towards 0 volt, right? In that case, again the system will move towards a stable state, and in this case the stable state will be 0 1, right? Rather than 1 0, it will be 0 1. So in summary, the cross coupled inverter finally reaches one of the stable states 0 1, depending on the noise value or the sign of the noise, whether it is in the positive or the negative with respect to Vm. And we don't know actually the noise, we do not know the characteristics of this noise, whether it will be positive or negative. Therefore it is impossible to predict that whether from given a metastable state or the state in which the input and output are Vm, whether it will finally reach to 0 or 0 1 state or 1 0 state, right? And therefore this is not a good system. This metastable state is not a state which we want in our design, because we cannot predict that what will be the output, whether it will be 0 or whether it will be 1. Additionally, we do not know that at which moment this noise will be triggered, and from the VM point when it will be actually going from 0 to 1, sorry, when will it be going to the stable states 0 or 1, right? So neither we can predict the value nor we predict the time taken to reach that value, and therefore for a designer this is, or for a design, not this is not a good situation, and therefore we should avoid metastable states. We should avoid reaching metastable state in a circuit, to make the circuit deterministic, right? We avoid reaching metastable state in a circuit, because if it is a metastable state, then the circuit behavior will be indeterministic or not predictable. Now we looked into the cross-coupled inverter pair, right? So for understanding memory action and various states, a cross-coupled inverter pair is a very good system. But in a real memory, we want that the change in state can be brought about as we want, right? So we can easily read and write values from the memory. So cross-coupled inverter pair has no mechanism to change the state as per our requirement, and therefore we use other types of memory elements, for example latches and flip-flops, or latches and flip-flops are the sequential circuit elements which are used as memories in the VLSI designs, right? So latches and flip-flops have extra pins that allow to change state as per our control signal, and the control signal is the clock signal or the enable signal. So in a latch we have 3 pins: the D pin, which is the data pin; the enable pin, which allows us to read and write; and the Q is the output of the latch. Similarly, flip-flop has got 3 pins. The simple D flip-flop has got 3 pins. So D is the data pin, Q is the output pin, and CP is the clock pin that controls the reading and writing of the data to the flip-flop. Now, what is difference in the functionality of a latch and a flip-flop? So in short, the difference is that the latch is level sensitive and flip-flop is edge sensitive. So let me explain this difference with the help of an example. Suppose we have a flip-flop and we have a latch, right? We have a flip-flop and a latch. So the clock signal that goes to a flip-flop is shown here, right? This is the clock signal, or the signal that goes to the enable pin of the flip-flop, and this is the data. This is how the data is changing, right? Now what will be the behavior of the flip-flop, right? So the flip-flop is edge triggered. So the value at the D at the clock edge gets propagated to Q, right? So where are the clock edges? So the clock, so suppose that flip-flop is positive edge triggered. So these are the edges. And at this edge, whatever the value was at the D pin, that will be written to the Q pin, right? So initially it was 0 at this point. So if with the output of the flip-flop will be 0, right? At this edge, the D value of D is Q, say 1, so the output will be 1, right? And then at this point the output is the value of D is again 1, so it will remain 1, right? And at this edge the D value at D is 0, so the value will change, the value at the Q pin will change as 0 for the flip-flop. Now what about the latch? So latch is level triggered, meaning that the value at D pin, when the clock is high or the enable signal is high, it gets propagated. So value at the D pin gets propagated to Q when the clock or enable pin is getting a high value, right? And when clock is high, latch is similar to a buffer, right? So let us see that what will be the waveform at the output of a latch. So the latch will produce the output, or it will be same as a buffer whenever the clock is high. So these are the region where the clock is high, or the enable pin of a latch is high. So in this region, whatever the value of D was, it will be available at the Q pin of a latch, right? And once the clock goes down, whatever this value was, that will remain there, right? Till the point again the clock or enable signal becomes high, right? So it will remain 1 here, and whenever it comes at this point, whatever the value of the data was, it will be reflected at the Q pin of the latch, right? Now once this point is there, then whatever that point gets latched, right? Whenever the clock goes 0, so whatever was the last value when clock was 1, that will be get latched, and then it will not change, right? Even if the D is changing here, the value at the Q of the latch will not change. Again, when the value of clock is becomes 1, whatever was the value at the D pin, that will be available at the Q pin. And whenever the when the clock signal becomes 0, whatever was the value, that will be remaining latched, right? So this is how the functionality of a latch and a flip-flop differ. Now let us look briefly into the internal details of a latch, like how it is implemented. So a latch can be implemented in a simple manner by using a flip multiplexer with a feedback, right? So this is a simple implementation of a D latch. So whenever enable is equal to 1, right? So whatever the value is at the D pin, that goes to the Q pin. And whenever enable is equal to 0, then whatever was at the Q pin, that is being selected and that is being recirculated to the output, meaning that it is a kind of it will remain in that particular state, right? So this what Q is going to the input, and again input is coming to the Q. So it is a kind of recirculating the old value, and therefore whatever was the last value, that will be recirculated or will remain at the output, right? So whenever the clock enable is 0, it is simply maintaining the old state, and whenever enable is 1, then whatever the value was at the D pin, that goes to the Q pin, right? So this is a simple implementation of a latch. Now let us look into the implementation of a flip-flop. So flip-flop can be implemented using two latches. The first one is the master latch and the second one is the slave latch. And notice that the master latch is having a clock signal which is going with a inverter, right? And to the other latch, the clock signal is going without any inversion, right? So now how does it perform the work of a flip-flop, right? So note that the flip-flop is an edge sensitive. So how do we get the edge sensitiveness in a flip-flop? So we get it as follows, right? Suppose the clock signal was clock signal was 1. Sorry, 0. Suppose initially the clock signal was 0, right? So it was 0. So if the clock signal was 0, then this inverter was producing a 1, right? So whatever the value of D was, that was being written at the output of the master latch. So whenever 0 was there, whenever the 0 was there at the clock pin, at that particular the value at the D pin of the flip flop, that is going and being available at the output of the master latch, right? Now what happens is that suppose the clock signal goes from 0 to 1. Now, when the clock signal goes from 0 to 1, two things happen. What are these two things? First thing is that this signal, this goes from 0 to 1, right? So this output of this inverter goes from 1 to 0. So now the master latch gets latched, right? So the values at the q pin will not change. Whatever was written, that will be available at the q pin, but its value will not change because now this master latch has been latched, because the value at the enable pin is 0. It has gone from 1 to 0. So now the master latch is no more transparent. It will not, it will, whatever the last value was produced at the q pin, it will remain stable at that, right? And the second thing is that this slave latch becomes now transparent, right? So whatever was last latched at this particular point, when the edge came, that will be available at the q pin of this slave latch, right? Note that the input is now not changing for the slave latch, and therefore it will remain stable. So in effect, what is happening, whatever the value was at the particular edge, whenever the edge was there, when the clock edge came, at that particular point, whatever the value was at the q pin of the master latch, that get produced at the output of the slave latch, and it remains at that state until and unless the next positive or rising clock edge occurs. So by the combination of values of the combination of enabling, or the inverted enabling of the master latch and the slave latch, we are able to achieve the edge based functionality of a flip flop. So this is how we can implement this is one of the simplest implementation of a D flip flop using two latches. Now for the flip flops and flip flops to work properly, we need to satisfy some timing constraints, and these timing constraints are known as setup and hold timing constraints, right? So we said that in a cross coupled inverter, a cross coupled inverter can reach a metastable state if the input is, say, Vm, right? So output will become Vm, and that is not a good state, because we do not know from that the metastable state whether it will reach to 0 or 1, right? Similarly, if these constraints are not followed for a flip flop, it can go into metastable state, meaning the output of this cube of the flip flop can be in a state which is intermediate between 0 and 1, and this state can finally go to either 0 or 1, we do not have control either over the timing of it or with at the final value of it, right? And this will happen only when the setup and hold constraints, or this can happen if the setup and hold constraints are violated. And what are these setup and hold constraints? Let's look into that, right? So around the clock edge, we have a forbidden window, right? So on one side of the on the left side of the clock edge, we have a setup time, meaning that, see, when the clock is coming at the clock pin of the flip flop, and data is also, that data can also change, right? So the setup and hold constraints it basically defines a forbidden window around the clock edge where no change in data is allowed, right? So there is on the left hand side, we have what is known as setup time constraint, and on the right hand side we have the hold time constraint. So what are these constraints? So let us understand them, or let us understand the definition of these constraints. So the first constraint is setup time. So setup time is the minimum amount of time the data signal should be held steady before the clock edge, so that the data is sampled correctly and deterministically. So before the clock edge, for this much time, the data is not allowed to change, right? So if there is any change in data, it should settle by this time. It shouldn't change over the forbidden window, right? So the forbidden window on the before the clock edge is defines the setup time, Similarly, we have a forbidden window on the other side, or after the clock edge. So what and that defines the hold time. So what is hold time? The minimum amount of time the data signal should be held steady after the clock edge, right? So after the clock edge, the data shouldn't change. The data, meaning the value at the D pin, shouldn't change for some time, right? After the clock edge, the minimum amount of time the data signal should be held steady after the clock edge, so that the data is sampled correctly and deterministically. So when we use flip-flops in our digital circuits, we should we should make sure, or we should ensure, that the setup time constraints and the hold time constraints are met, right? So the meaning that the data which arrives at the D pin, it shouldn't change in the forbidden window, which is defined by the setup time constraint and the hold time constraint. So if these constraints are violated, then a flip-flop can go into metastable state. And we used various kind of EDA tools, or electronic design automation tools, and a timing analysis method, which is known as static timing analysis method, to ensure that setup and hold time constraints are not violated for a flip-flop in a digital circuit. So these are a few references which I have used in preparing this lecture. Now, to summarize, in this lecture, what we have looked into sequential circuit elements. We started with cross-coupled inverter pair, and we saw that there are three states for a cross-coupled inverter pair. The first one is the zero state, the second one is one state, and third one is the metastable state, or VM state, right? And we saw that metastable state should be avoided in a digital circuit, and why it should be avoided. Then we looked into two basic type of sequential circuit elements which has read and write capabilities. So those are latches and flip-flops. We saw the differences between them and their implementation, and then we saw the constraints of setup and hold for a flip-flop. So that's it for this lecture. Thank you very much.